Hey there, team. So now I'm going to do the short answer questions for Chapter 15 formative. Let's have a look. So here says the Houndsworth Town Sports Association is planning a sports carnival. Traffic through the town will be diverted around the sporting venues during the carnival. Okay. The network below shows the roads that can be used during the carnival represented by edges and the intersection of those roads shown as vertices. Okay, cool. The number of the edges are the maximum number of cars that can travel on the road each hour. Okay, so it's cars per hour. And the roads will be restricted to allow one-way traffic only, as shown by the arrows. Okay, so the arrows will indicate one-way traffic. So essentially, you have to pay attention to the arrows, but it looks pretty direct. It's from A to I. How many cars per hour can enter the diversion roads? So, how many cars right here? So how many cars can go through? So you get 180 cars per hour. There you go. So how many cars can enter the diversion? 180 cars per hour. Cut number 1 is shown on the diagram above. Okay. If the capacity of cut 1 is 150, what is the value of M? So if this is cut 1, which you can see here, that means the edges that are being in question, or at least the things you should be looking at, is edge from this edge, this edge, and this edge. And we know, remember, cutting from the source and the sink, the source is on this side. So this is source, whilst this is the sink side. And we can see that it's all flowing from the source. So you will include the 90. You will also include the 40. And you also include the value M. And they should all equal to 150. Okay, because they said the capacity of cut 1 is 150. So in total, 90 plus 40 is 130. 130 plus M has to equal 150. So therefore, M must then be 20. And so that will indicate 20 cars per hour on the route from B to E. Okay. And then moving on to the next question. Maybe I should just change that to keep it all nice and consistent. There we go. All right. Next one. Show that the smallest value of M that will ensure there will be no buildup of cars at intersection B is 50. This probably needs a bit of grammatical correction. Smallest value M. So probably like that. So if they're really just trying to say, show that the smallest value of M is 50. That's what they want you to do. But where is M? And ensure that there will be no buildup of cars at intersection B. So really, they're trying to say that at intersection B, I'm just going to focus on it. So this is where B is. At the intersection, to make sure there's no traffic, all right, because you've got 180 cars. Remember, 90 cars going that way, 40 cars are going this way. That's 130 cars that are being sorted per hour. What you're missing right now is an extra 50. But remember, M was 20, so that was a problem. So what is the smallest value of M so that it ensures that you can have a smooth traffic without any build-up at this intersection so no one's waiting? Well, the smallest number for M has to clearly be 50. Onwards. So it could be 60, it could be 70. The more, the better. But really, minimum at the moment, it's 50. Okay, so how do you answer this question? How do you show it? Well, we know that since it needs to add up to 180, that's the flow coming in, right? So the smallest value has to be then 90 plus 40 plus M instead of equaling to 150 before, we need it to be 180. Okay, and so therefore you can see M is equal to 180 minus 130, which gives you a total of 50. And that tells me, therefore, 50 cars per hour. All right. Next one. Where am I up to? Capacity of the road is section B. E is 50. M equals 50. What? The capacity of the road between intersection B. Oh, so they changed it to 50 now. Okay, yep. The maximum flow through the network is currently 150 cars per hour. Okay, yeah. Probably going to highlight that. The max flow through the network currently is 150 cars per hour. Clearly mark in the cut that determines this max flow on the network above. So what they want you to do is to do a minimum cut to show that the max flow is actually 150. So going back to your diagram, how do you find your minimum cut? Remember, when you're doing your cuts, you're trying to look for, and remember cut 1 was, or M is 50 now. Cut 1 will be 90 plus 40 plus 50, which gave you 180. Okay, so cut 1 would have gave you 180. You're trying to beat 180, trying to get down to 150. So what kind of cuts can I do? Now think about, when I do cuts, you're looking for the smallest value. So I can see there's a 40, there's a 30, and there's an 80 there, right? The aim is to separate the source from the sink completely. So in my mind, I'd probably go for something like this. You see what I mean? Like if I cut it like that, you know, cutting just those edges. So if I cut the edge of B to D, I cut the edge of F to H, and I cut the edge of E to H, there's no way any car can get through to the end, okay? Because I've separated them. True? You can't go center, can't go top, can't go bottom. So that would be probably, I think, the smallest cut I can do. 80 plus 40 is 120. 120 plus 30 is 150. There you go. But that's how I look at it for cuts. Okay, I try to look for the smallest value where possible. So when you're doing cuts, remember to do dotted lines to show that they're imaginary lines. So here we go. We're going to do a nice dotted line all the way across, and that gives me cut 2, where you have 80 plus 40 plus 30, and that gives you 150. Okay, there you go. So that's how we would have done that one. And then question 2C done already. And then 2D, if the road between intersections F and H was improved, what is the minimum extra capacity it should take to solve the potential traffic buildup at F? Oh, I need to look at the diagram again. Well, I like a clean one, but I'll just work with what I got here. Let's just print screen this and paste. All right, let's have a look. What do they want us to do? So the Sports Association have noticed that there could be a buildup of traffic at intersections E and F. Where's E and F? So E and F are currently at, this is E and F. So there's potentially build up at those intersections there. Okay. If the road between intersections F and H, okay, was improved. So F and H now. So it looks like I'm now looking at something else. So F and H, which is this one and this one, were to be improved. All right. What is the minimum extra? So minimum extra capacity it should take to solve the potential traffic build up at F. What? All right. So now they want you to look at the extra capacity that it should take to solve the potential traffic build up at F. Well, build up of F. So we have to look at the flow then. So at the moment, say 180, 90 can only go through here. So that means here's 90. So 90 to, well then this is currently 80. So I guess if F can, to increase this flow, if F can now take an extra 10, which means 90 by 90, and that should flow better. Is that what they're trying to say? Wait. The road between intersections F and H was improved. Okay. What is the minimum extra capacity it should take? Yeah. Extra capacity, it should be 10, an extra 10. So it should take to solve the potential traffic buildup at F. Yeah. So when they say F and H, they're essentially talking about this edge, and they want you to find the value or the edge, the minimum value that it should increase to. So from 80, how much should that section increase to minimize buildup of traffic? And so we already know that 90 was going through here, and therefore 90 will go through there. And then if we can increase this by an extra 10 as a minimum, well, you will then increase the flow from that section there. So here you would say minimum required is 10, I should use the right color, 10 cars per hour extra capacity. And that answers D. Going on to E now, what is the minimum in order to solve the potential buildup of traffic at intersection E? Okay, let's look at the diagram again. So E is over here now. Okay, open another road from intersection E to D. E to D, where is D? Oh, D is over here. All right, so D is over there. We're not going to look at this now. D. So what? E comes this way, so E to D would mean the flow has to be this way. So E to D, and what does that mean? What is the minimum capacity of this road that will avoid traffic build up at intersection E? Well, at intersection E at the moment, we have a value of 50, right? With this new road, this intersection E connects to D, which is an extra 50. But then this is already 40, so 50 plus the 40 is 90, and that only takes 70. So, I guess the answer here would then be we would need an extra 20, because that's now saying 50. Yeah, so if I draw it again, sorry, the diagram is just looking a bit messy for me. Essentially, I'm saying from B to this point, that's 50. So that means a new road that's being created will connect to that point there. So that means this 50 value will now become an extra 50 this direction. But then if that's 50 here, and then 40 plus 50 is 90, you can already see 90 and 70. If we can increase the intersection at this point to an extra 20, then that will accommodate the 90. But that still creates a problem over here too, by the way. But I guess they're asking, what is the minimum capacity of this road that will avoid traffic buildup at intersection E? At intersection E. But intersection E connects to D though. Yeah. So they're really saying that what is the capacity at D? So another road from intersection E to intersection D. What is the minimum capacity of this road that will avoid traffic buildup at intersection E? Well, the only way is an extra 20. So the maximum capacity of this E to D, if it was 20, 40, 60, that should solve the problem. Yeah. 50 goes there, so then therefore the edge is an extra 20. What is the minimum capacity of this road that will avoid traffic buildup at E? Oh, sorry, I got confused. Okay, no, I understand what they're saying now. I keep thinking I'm trying to solve this issue here. No. What they're asking us to do, apologies, what they're asking us to do here is this road E to D, they don't know the capacity for this one. They don't have a capacity value. So whatever this value is, let's call it Y. They know that the 50 is coming here, but we don't want any traffic at intersection E. So at intersection E shouldn't be any build up of traffic. 30 can only go that way, so clearly this has to be then 20 there. I was thinking 50 here, needing 20 to go there, but now I understand what they're trying to say. So 20 is your minimum value there. So 20 cars per hour at that point. Okay. And then explain why a road intersection E and D cannot solve potential traffic build-up in the network, which is probably what I was thinking just now. The potential network, so even though this is 20 minimum, 30 goes there, 20 goes here, you still get, let's say 20 is a minimum. It can be more as well. The problem is that this is already 60, and we found out as I was solving it before, I noticed that there's a problem here. This only takes 50. So here's the problem. I only can get, at the end of the day, because this is going to be 50, I need 50 to go through. But to get 50, that means this would have to be 10. But if this is 10, there's going to be a buildup of traffic here because this is already 30, if that makes sense. Okay, so here can only take 20, but then if I put 20 there, 20 plus 40 is 60, but 60 is already too big by the time they get to G. Okay, and that's an extra 10 already. So there's always going to be a build-up of traffic there, so hence why they say, explain why a road between intersection E and D cannot solve potential traffic build-up of the network. You should be referring to the capacity at the intersection D, so I would say something that at intersection D, there'll be a minimum. Oops, let me just write it again. A minimum of 60 cars per hour flowing through. So this would imply that therefore there will be traffic buildup at intersection was it G? Yeah, at intersection G, because the capacity of intersection G to H is 50 cars per hour. So this would mean too many cars, or the larger value of capacity. So too many cars. Okay, 60 cars. Number of cars flowing through or passing through is larger than capacity. Hence, and this is a long answer, hence potential. I guess as long as you include the capacity, the aim is to mention about D, 60 cars per hour, 50 cars per hour with G to H, and that it is larger. Okay, so in some ways you need to show that you understand that the flow coming in is going to be bigger than what it can take. Therefore, there will be hence potential traffic build-up. Okay, so that's how I would explain it. So 1 mark, I'll probably just be looking if you've ever referred to 60 cars per hour or G to H, or you need to have reference to the key parts of the network, why the E and D doesn't solve the problem. Okay, there you go. And then are we up to almost there? 3 more pages. Here we go. So on to the next one, question 3A. Question 3A, they want you to use Hungarian algorithm. Oh, wow. Okay, cool. Complete the Hungarian algorithm and write down the modified cost matrix. Okay. Let's see. So, Hungarian algorithm, they normally say that you do the row reduction first before you do column. I usually just look at the rows and columns. It doesn't actually matter which one you do first. You look for the numbers that are most similar so that when you subtract them, they're more likely to end up at 0. So I can see here, if you look column-wise, see how they're all 70s? Notice how those are 70s. And this is, that will probably not cancel out well, but these are relatively the same. Whereas if you go row first, see 90, 70, 70, there's more differences between them than similarities. So I'll probably, in this case, I would have gone for a vertical reduction first. And it doesn't really matter which one you do, but that's what I'm going to do first. So I'm going to subtract column first, and it may be unconventional. Maybe you get a different answer, but your final answer and my final answer should be the same. So the first thing is I'm going to subtract the smallest value in each column, and I can see 71 is the smallest value there. 74 is the smallest value there. 62 is the smallest value there. And 93 is the smallest value there. So if I subtract them, this should give me 0, 0, 106 minus 93, so 7 plus 6 is 13. Oh no, smallest value is 83, 84. What am I doing? Woo. Already made a mistake. So that would be 0, 84, so 6 plus 10, that's 22, I think. Is that right? I'm not using a calculator here. 6, 10, 16 plus 6 is 22. Yep. This is 6 plus 3, which is 9. 9. Take away 62. This is 0. 8. 15 plus 8. 15 plus 8 is 13. 62, yeah, this doesn't work out too nicely in these 2 row columns here, but at least it works well for the next next 2. So 91 take away 62. What's that? 8, 11, 9, 29. 74 take away 62. 8 plus 4 is 12. There you go. My next one is take away 71. So that's 1, 0, 1, And 91 take away 71 is just 20, isn't it? 20. 74, that gives you 0, 4, 5, and 74 take away 8. So 6 plus 8 is 14. Assuming I haven't done any mistakes there. So that's my rows. And oh, wait a minute. Does that mean 1, 2, 3, 4. So you got 9, 22, 9, 0, 0, 13, 29, 12, 1, 0, 1, 20, 0, 4, 5, 14. What can I do? So from here, can I draw 4 lines minimum? Or can I do it all in 3? I can do 1, 2, and 3. So that means I still have to carry on with the algorithm. So I've done the columns. Now I need to do the rows. So let's subtract the rows now. Let's have a look. Row-wise, the smallest value is 1. So minus this by 1, minus this by 4, minus this by 1, and minus this by 12. All right. Well, that will give me a new one where 1, 2, 3, 4. If I minus by 1, that's 8, 0, 0, 0, 0. Wow, I've got a lot of zeros now. 13 minus 4 is 9. 22 minus 4 is 18. 9 minus 1 is 8. Minus 1 is 28. 0, 4. 0, 0. Oh no, what am I doing? Sorry, I was meant to subtract the, not all of them by, I need to subtract them by the row without any zeros. So clearly, that will give me a new one. 1, 2, 3, 4. That should give me 9, 0, 1, 0, 22, 13, 0, 4. That gives me 8, 0 there, 28, 4, 0, 12, 20, and 14. Complete the Hungarian algorithm and write down the modified cost matrix that will allow an allocation of each swimmer to an event. Let's see, can I do all of this? I can do 1, 2, and 3. So no, it looks like I have to continue with my algorithm again. So my next algorithm, so let's go 1, 2, 3. If that was my 3, then you will subtract from the smallest value for them all. Okay, so the uncovered ones and the ones that are being covered, the ones that have a double, you add the value. So here I would say subtract 4, subtract 4, subtract 4, subtract 4, subtract 4, subtract 4, and add 4 to those two. So that gives me a new page. 1, 2, 3, 4. So 9, 0, 5, 0, 18, 9, 0, 0, 0, 0, 14, 24, 24, 12, 0, and 4. All right, so let's see if I can get my, so I can do 1, 2, and is, yeah, so there we go. So this is my matrix finally. So you got Alan, Bruno, Chris, and Dirk freestyle, backstroke, BR, and BU for butterfly. So if I had to do the allocation, which is in the next one, write down 2. So there should be 2 possible allocations, and I can see that. Keep in mind that you might have got a different answer to what I got because I did column. I probably should have just done rows and then columns because that obviously screwed me over there in terms of following to script. Maybe I should do. So if you did it by columns and then you did rows, this is what you should have gotten. If I should do the other option too. I should have just stuck to the Hungarian algorithm that's taught in your textbook. I just thought I'd go a bit slower. I thought it would reduce the number of steps I had to do, but all right. If you did the other way, if you subtracted by the rows first, which is the way textbook taught you, then you would have got the smallest value to subtract is 62, 71, 72, and 74. So when you subtract them, you would get then, this is 10, 0, 74, take away 62, 8 plus 4 is 12, 62 plus 30, so that's 31, I think it is. And then 71, so this is 7, this is 0, 85, 9 plus 5 is 14, and plus 30 is 101, so 35. 72, this is 0, so 72. 79 take away 72 is 7. Is that right? Yeah. And then add 20s. If I get 71 plus 72 plus 20 is 92, so 19. Plus 20, so 21. Yep. And then the next one, 74. So that's clearly an extra 10. That's going to be 0. 74 plus 20 is 90. So take away 3, so 17. 74 plus 10 is what? That's 14. All right. So if you had done it this way, then the 4 columns you're starting off with is 31, 0, 10, 12, 35, 14, 0, 7, 21, 19, 0, 7, 10, 0, 17, 14. And then you check if you can cover all the zeros with the number. And I can see that if I had just done that, I would have been sorted already. So what do you need to do? You need to now make sure every column has a 0 in it. So I would minus this by 10 and I'd minus this by 7. So that will give me 0, 0, 7, 5. Okay, and then this one would be 21, 25, 11, and 0. Okay, so your new table should look something like this. So you should have 21, 25, 11, 0, 0, 14, 19, 0, 10, 0, 0, 17, and the other one's 5, 0, 0, 7. Okay, so if you did do this, let's see if we can cover all the zeros. We can do 1, 2, 3, and yeah. Oh, wow. So that means you didn't even have to do the intersection. So maybe your row method was better than my crazy idea of doing columns first. Usually that could reduce the number of methods that I would have done. But interestingly enough, we should still have the same 0 problem. Okay, same 0 ideas. And you can see here your allocations will end up similar, because the key part, notice here, is that these two are the same. See that? So your allocations will end up meaning it has to be, there's only one way to do it, but let's go with, I'm assuming that this is what you would have done. So if we did this, this is Alan, Bruno, Chris, and Dirk, and freestyle with backstroke, breaststroke, and butterfly. So allocations are, if we do A, B, C, and D, and then BA, sorry, should be F, BA, BR, and BU. Looks like allocation for A can only go to backstroke. B can do breaststroke and butterfly. This is where it's going to be good. So you can see that C can also do the same, 1 and 2. So that means that's where the two allocations will come from. And then D looks like they can do freestyle or backstroke. But right there, you can already see that because A can only do BA, you have to allocate Alan. A has to go to backstroke. That's the only allocation you can do. And then B, this is where B and C has options. B could either be breaststroke or butterfly. And then same thing, C can interchange depending which one they choose. So it could be butterfly or breast. Okay, and then that would imply that once those are taken, or even if you think about it, because A is taken backstroke, then that means Dirk can only do freestyle. Does that make sense? Can you see? Because Dirk only has freestyle or backstroke, but since A can only do backstroke, you have to give A backstroke, and that means Dirk gets freestyle. And your two allocations that can swap are these two guys here. Okay, so your answer for the write down two possible allocations, you should write them out clearly. So A could be, the option is backstroke, Dirk was freestyle, and the ones that play around was B could be breaststroke, and then C can then be butterfly, or your other option was that A can still be, has to be backstroke, D has to be freestyle, and then B could now be butterfly, and C can be breaststroke. Those are your two allocations there. I'm actually interested. I have a feeling I might have made a mistake with my calculation here, but let's see if my allocation would have worked as well. For those who aren't interested, maybe fast forward. I'll get to the other questions later. I'm just interested in seeing what I would have got. So A, B, C, and D. B, A. Whoops. F. F, B, A, B, R, B, U. So according to this, my allocation is A can be backstroke and butterfly. Interesting. D can only be freestyle, and then in this case here, the two people that play around is B can be breaststroke, B can be butterfly, C can be breaststroke and butterfly. Oh, so this is interesting. So clearly, Dirk can only be with freestyle. So D is only with freestyle. Now, the problem is that there are so many people at butterfly and breaststroke. That's why A shouldn't be butterfly, because if A is butterfly, And that means that B can now only do breaststroke. But if that's true, C can't do anything. So that's why I can't allocate A to butterfly at all. So you can't have A being in this battlefield here because B and C can only do the same things. So they have to compete with each other. Therefore, A has to go with backstroke. And then my two different allocations, B is with breast, C is with butterfly, and or alternative. Okay, but that's the reasoning. Oh. Well, kind of similar answer. Actually, the same answer. Oh, we end up with the same allocations. So it looks like, no, I did do it right. It does look more confusing doing mine. So maybe don't do what I was telling you. Just stick to the algorithm that they teach you. Do row reduction, then column. But with my one, it seemed like you'd have to do a bit of thinking. But in all of them, you have to do a bit of thinking. But hopefully that shows you that it didn't matter whether you did row or column first, you still get the same answer. Okay? All right, let's move on. I think I spent a bit too long on that one there. Let's go. So planning for the opening ceremony of the sports carnival involves 7 individual processes, A, B, C, D. Okay, whoa. Good network. Okay, what is this? In an incomplete activity table, okay. For the opening ceremony project is also shown with one edge missing and an incomplete forward. Okay, yep. All right. So, which activity cannot start until E has been completed? E, well, G needs to wait for E to complete because G connects right after E. So if E doesn't finish, G can't continue. So the answer is G there. The activity network requires the use of dummy activity. Complete the activity network above by adding the missing dummy edge. Why is that? So the only way to know is you have to look at the table, the precedence table. So A should be by itself. That is correct. B is connected to A, which is correct. That is true. C is connected to B. That is correct. C is connected after B. D is connected after A. No. Oh, yes. That is correct. And E is connected by B and D. No. So E is connected to D, but it's not connected from B. So the dummy has to then be down this way. So there you go. So here we go. We've got, and draw the arrow, and I would encourage you to write dummy. That's the convention. And normally we write dummy, comma, B so that people know it's coming from B. But you can draw the arrow and that's good enough as well. Okay, so I've done 2B. Okay, yeah. Moving forward. Oh, they never got me to fill out that table. No, maybe not. Below shows the earliest starting time, latest starting time, and duration days for the events. 3 of the values in the table are missing. Oh, no, maybe I do need to fill it out. So here we go. Let's screenshot this so I can bring it down and work with it. So here we go. It's coming down, and I'm just going to paste it here. There we go. Okay, so what do we have? What do we have here? So to calculate this, A has a duration of 2, so I'm going to write 2 here. EST, yep. B has a early start time of 2 and later start time of 4. Okay, so what we see here, this box here is the box for D. I'm probably going to make it a bit thinner. Whilst I need to think of a box over here for B. The earliest start time for B is clearly 2. And they said the latest start time for B is 4. Interesting. So this is 4. So according to this, from 2 to get to the next earliest start time for C is 7. So B then has to be a capacity of 5. Okay, so did I feel? Yep, so this should be 5 here. I'll probably do it in pink. 5. And that would then mean 4 adding 5. Oh, technically something minusing 5 gives you 4. It has to be then 9. 9 has to go here. Let's see. C is 4 and 7. Oh, wait. Duration. Oh, C is a duration of 4. I should fill out all the durations actually. D is 8. D is 8. E is 2. F is 2. And G is 3. Okay, so let's work backwards. 13 minus 4, yes, that is 9. Okay, I was lucky there. I didn't double check that, but yes, that is 9. So then 7 plus 4, that means this is 11. And does that mean I filled it all out then? C, latest start time for C is 9. So 7 and 9. And activity F, earliest start time is 11. There you go. Oh, I figured it out already. All right, well, there you go. So that's how you do. I was just doing forward scanning and backward scanning there for those who weren't sure. And what was missing there is that green box. That's the green box for the direction of B. This box here that you see is the direction of D. So early start time is 2 and later start time is 2 for D. So essentially they're trying to tell you this is a critical path. So 0, 0, 2, 2, 10, 10, 12, 12, 15. That's a critical path is what they're trying to say. Okay. All right. So, I just highlighted the critical path too. Doing all this by accident. So A, D, E, G. It just so happens as I'm describing what we're doing, I'm also answering the question as well. What is the float time for activity B? Well, float time, activity B, you can see here, that's the missing box that I drew in. You can see the latest start time for B is 4 and the earliest start time is 2. They have a float time of 2. Or if you filled out the table correctly, these two here will tell you the float time. So they don't have to start at 2 to get everything on point. Because it only takes a duration of 5, 2 plus 5 gives you 7. And then 7 plus 4 is 11. 11 plus 2 is 13. But remember, the minimum required time is 15. So you still finish early. Or what could also happen is B could say, I'm going to start at 4 instead. So 4 minutes in, 4 plus 5 gives you 9. 9 plus 4 gives you 13. And then 13 plus 2 still gives you 15. I still finish it on time. So that's why they didn't have to start exactly at 2. So right after A finishes, which is after a duration of 2, they don't have to start immediately. They can wait an extra 2 minutes or 2 hours or whatever the duration represents. That's when... Actually, I should know the duration. I should look at it. What is it? Does it say... Oh, they don't tell you if it's in hours or minutes. Or in days. So duration's in days. So they can wait an extra 2 days and they can still finish on time. So float time is LST minus EST. So that equals to 4 minus 2 gives you 2 days. Don't forget to put the units. Okay, and then, this is it. The last question. If activity C was delayed by 3 days, what is the overall completion time of the project? Delayed by what? If activity C was delayed by 3 days, what is the overall completion time of the project? So activity C, well, if activity C was reduced by 3, it's not on the critical path, as you can see. So if you reduce that time by 3, so it makes it 1, all it changes is the starting times for all of these guys here. But because it doesn't... wait, did it say duration? delayed by 3 days. Oh, sorry, not reduced. Delayed by 3 days. Well, then that's plus 3, so it makes it 7. Oh, that could change things. So the reason why, because I thought it was reduction. If it's reduction, it doesn't change the overall because the minimum time required is still 15. But by adding 3, it might change the critical path. So let's have a look. If it is 7, you will now have A, which is 2, 2 plus 5, which is 7. And then from here, 7 plus 7 gives me 14. So this now changes that to 14 as earliest. 14 plus 2 is 16. So that now becomes the new critical pathway. So then you'd have to look up this way. So it will change the minimum time required. So initially it was 15, but now I need 16 days to complete it if it was delayed by 3 days. So the answer would be 16 days for the overall completion because that's the new critical pathway. So if that becomes a new critical pathway, that will change just a few of the float times and all that. So it will become 7, 7, 14, 14, and 16, 16. But that question wasn't asking you to do all that. The question is just simply asking the overall completion time. But because the keyword was delayed, it means that you add on the extra numbers. But there you go. So this is a pretty long video here, and that's probably because I'm kind of winging it, just doing it for the first time. So a couple of it took me a couple of mistakes like this one. I was trialing an error with a different method. Clearly that took me off, and just a few others. But hopefully this helps you understand a bit more. I would say that this is not the best crashing question. Your textbook might be good, or just watch my videos on the VCO exam questions. That could help you understand that better. This is, to me, is the bare minimum of understanding crashing, which is why it's a formative, right? But to do the SAQ, you should really learn EST, LST, and crashing. So this is probably the beginnings of it all. So by changing, even in that question there that we just did, that last one, you should learn how to, if that changes the critical path, then you need to be able to recalculate EST, LST. But not only that, what's interesting is if they start talking about what if I reduce, what's the minimum time needed to reduce minimum cost and all that, the VCO questions are good to practice. Okay, so I'd say this is just a preliminary practice. If you've done the formative, that's great. That's a bare minimum. I'd say start doing the practice SAQs. Okay.